This video covers rolling and slipping. In all the situations we've seen up until now, we've dealt with objects that were rolling without slipping. What that meant is that they were moving forward and rotating at the same rate that it was moving forward. So a way to visualize that is if you had an object that had a point labeled on it, and again it's moving forward, and then it is also rotating, the distance that it moved as it rotated from here to here, let's say, would be the same distance from here to here. Again, so we were able to use this relationship V equals R omega because they were rolling without slipping. In these situations, we're going to see objects that are rolling with slipping. What that means is you can no longer apply this V equals R omega right at the beginning. An example of that is when our velocity of our center of mass is less than R omega. You can imagine a burnout or burning rubber. So what happens is that your tires are spinning very fast, but again, it's not moving forward just yet. So we are rotating faster than we are moving forward, than the center of mass is moving forward. So again, this relationship does not stand. Another example is when your center of mass is actually moving faster than we are rotating. So again, something like an object that's sliding across, but a point on it is rotating much slower than the object is moving forward. So again, you see this point has not moved very much in its rotation, but it does move forward a lot faster than it is rotating. And then again, this last example down at the bottom, when you are rolling backward, when your center of mass is moving forward, but your rotation is opposite of that. So you can imagine a backspin in billiards. What that means is you have an object that is, again, moving forward, but you have a backspin on it. So it's rotating backwards, but it still continues to move forward. So the thing to remember in all these situations is that it's eventually going to reach this V equals R omega condition. So that the way we solve these problems is pretty much going to be the same. And again, this situation is not as common as rolling without slipping, as you'll see in the next problem. In this example, we have a bowling ball of mass m and radius r is thrown such that the instant it touches the floor, it is moving horizontally with a speed v naught is equal to 5 meters per second, and it is not rotating. The coefficient of kinetic friction between the ball and the floor is 0.08, and we're asked to find the time the ball slides. Here we're given our information as the moment of inertia is equal to 2/5 mr, and this is a squared. So rewrite this as 2/5 mr squared. And we can assume that this moment of inertia is about our center of mass. Again, in this situation, it flat out tells us that we are sliding, and this object or this bowling ball is going to continue to slide until it begins to rotate at V equals R omega. So we can start by looking at the information we're given. It says that V naught is equal to 5 meters per second. And again, it's not rotating when we begin. So V naught is equal to 5 meters per second. And omega naught is equal to 0. We're also given that the coefficient of friction is 0.08. And we have our moment of inertia as 2/5 mr squared. So what we can do is start with a function for our velocity. So we can say that our velocity as a function of time is going to be equal to V naught plus a t. Again, what we're trying to do is solve for t here. Here, you can see that we don't have an expression for A, and we don't have an expression for V just yet. But if we go to our Newton's laws, we can say that friction is acting on my object as it moves forward. So again, this is not entirely a free body diagram. I'm showing my center of mass velocity here and my friction acting down at the bottom. So my friction is going to be equal to my mass times acceleration. These are the net forces in the x direction. Again, friction can be written as mu times my normal force, or in this case, mu times mg is equal to mass times acceleration. And here you can see that the masses will cancel out, and you're left with an expression for your acceleration. Again, the goal is to solve for time, so what we need to do is find an expression that will replace this v. We said that this object is going to continue to slide until our final velocity reaches r omega. When it happens, it's no longer just sliding, it is rotating without sliding. So v will be equal to r omega when that happens. But now what we need to do is solve for omega, and that's going to be our final angular velocity. So we can go to our rotational equations. Go ahead and use some different color here. Omega is equal to omega naught plus alpha times time. Again, we said that we began with 0 rotation, so that piece goes away. And same thing, we need to solve for an expression for alpha. For that, we can go to our torque Newton's laws. So here, torque is what's providing my rotation, and we have friction, which is mu mg, times r. So remember that torque is equal to rf sine theta. In this case, friction and r are perpendicular to each other, so we can drop the sine part. And again, all of our sum of our torques is equal to I alpha. With all my substitutions, I can put in 2 over 5 mr squared and leave alpha there for now. The masses will cancel out, and you're left with one of the r's that also cancel out. You're left with 5 mu g over 2 r is equal to alpha. So if I go back and make that substitution, for alpha, I have an expression for omega with respect to time, and I have an expression for velocity also with respect to time. So what I can do is, because I said my final velocity will be equal to when my omega is equal to this equation down here, I can actually make that substitution in now. So we have r, and I'll change this to a capital R so we can be consistent with our radius. Omega is 5 mu g over 2r. And again, just rewriting all of our other pieces. Now you can see that our r's will cancel out here. And, oops, I dropped a time. And we have a time on one side, time on the other side. From here to the end, it's really just combining our t's and getting them by themselves. So I can move this piece over to the other side. Find a common denominator. This simplifies down to 7 mu gt over 2 is equal to v naught. And again, I want to solve for t, so I can rewrite this as v naught is equal to 2 t is equal to v naught times 2 divided by 7 mu g. At this point, we have all of these values. Once you plug everything in, you should get 1.822 seconds. This is the time it takes for it to travel before it begins to roll without slipping.